So exponential growth has many, many real-life applications. So many things grow exponentially. And one of the most important or most frequent uses that you'll see is money. Okay, so money in a bank account grows exponentially. And we use generally compound interest. So suppose you invest $100. We call your initial investment the principal. And we invest that in a bank account that pays interest of 10% per year. To compute the amount of money we have at the end of 1 year, we have to know how often the interest is credited. Okay, so how often the bank pays us interest. We use the word compounded. So let's say it's just once per year. At the end of once after your money's been in the bank for 12 months, your bank gives you 10% interest. Okay, so to increase a number by 10%, you would multiply by 1.1. Everybody knows this, right? Because 1 represents you keep 100% of it, and the 0.1 is plus 10% more. So 100 times 1.1, now we have $110. Okay, so for the privilege of being allowed to hold our money for a year, the bank paid us $10. But now suppose that the interest is going to be compounded twice per year. So instead of paying you 10% once, they're going to pay you 5% twice. They're going to break the year into two 6-month periods and pay you interest at the end of each period. So we take our 10%, divide by 2, that's 5% interest at each compounding. So at the first compounding, you multiply your 100 times 1.05, and now we have $105 in the bank. And at the end of the second 6 months, now we earn 5% on $105, not just on the original principal, but on the original principal plus the interest you earned. So now you're earning interest on your interest. That's why we call it compounding interest. So we take our original $100, multiply by 1.05 at the first 6 months, then multiply by 1.05 again at the end of the year, and we end up doing 100 times 1.05 squared, and we make $110.25 is our new balance. So how much extra money did we make by compounding twice instead of once? 25 cents. We made an extra quarter. By the way, you all know, I'm assuming, that you use either the decimal point or the cent sign, right? That says that's a quarter of a penny, right? Yes. I actually saw around like the Super Bowl or some big sporting event, there was a huge sign at Arizona Pizza that said wings, this much per wing, and it was written like that, 0.25 cents. And I was like, I'm going to hold them to that. Somebody made a mistake. You could try. I think that if somebody pointed it out, they would have to honor it. I mean, there's a giant sign that says that's the price. I don't know. So anyways, we made an extra 25 cents. So suppose we compound quarterly instead of yearly or twice a year. We're going to compound 4 times per year, every 3 months. So we take 10%, and instead of paying 10% once, we're going to pay 2.5% 4 times. Okay, so we're going to each quarter multiply our $100 by 1.025. So we're going to multiply by 1.025 4 times. Okay, so we multiply by 1.025 to the 4th, and that will give us okay, 100 times 1.025 to the 4th, $110.38. So we make 38 more cents than an annual compounding, but only 11 more cents than the twice annual compounding. All right. What if you were going to compound monthly? Discuss in your groups. How much money would you have at the end of a year if you compounded 12 times per year? All right. So they're going to pay us our interest monthly. They're still giving us a 10% quote. They're saying we're going to pay you 10% per year. That's called the APR, right? The advertised yearly interest rate. But because they're going to compound more frequently, they're going to pay us every month, we're going to have to work out our monthly interest rate. So that's going to be 10% divided by 12, right? They're going to take the 10% and break it into 12 equal installments or payments. So we do 10 divided by 12, and we get 0.833%. So that's what we're getting paid, less than 1% each month. Okay, so it's very tempting to just leave it like that, to forget that that's written as a percent because it's already a decimal. But this is a percentage. To change to a decimal, you move the decimal point to the left. So this is 0.0083 as a decimal. So to increase by 0.833%, I have to multiply by 1.00833. So I'm going to take my $100, increase by less than 1% each month for 12 months. So let's see, divided by 100. Oops. All right, so I got to take this number, 1.00833, raise it to the 12th, then multiply by 100, and I get $110.47. I got 47 cents. You might have rounded, right? I had my calculator not round anything, which is generally what you should do. You don't want your bank making random roundings that's going to gyp you of 4 cents, right? So you don't round anything until the very last step. And then you always round it down because the bank's always going to not going to give you anything for free. Although if they were calculating your mortgage payment, they'd probably round it up. Okay, so there's monthly. So these are all the calculations we've already done. We compounded once, twice, 4 times, and 12 times per year. We earn a little bit more each time. So we went up by 25 cents, then 13 cents, then 9 cents. So each time we compound more, we make a little bit more money, but the amount we're gaining gets smaller and smaller. So in general, this is the calculation that we've been doing. You take your 10% divided by n, the number of compoundings, add it to 1, raise it to the number of compoundings, and multiply by 100. So you don't need to know that formula. I mean, you've been doing that in general. So we take our 10% divided by n. We could write that as 10 over n, but then we just have to change it to a decimal afterwards. Right? We add 1 to that, raise it to the n power, because we get paid that interest rate every compounding, and then multiply by your $100. Now, what if I want to keep my money in the bank for longer than a year, though? All of these examples have been how much money is in there at the end of 1 year. Well, this is my annual growth factor. Okay. That's the number I multiply $100 by to see how much is there at the end of 1 year. I use that growth factor year after year after year, that same growth factor. So I'm going to take my $100, multiply by my yearly growth factor, t times for t years. So I raise my growth factor to the t because I'm going to repeatedly multiply by it. And then when you raise a power to a power, you just multiply the exponent. So I have 100 times 1 plus 0.1 over n to the NT. So this is how I would calculate the amount of money in the account for longer than a year. And I can generalize this. My $100 is my principal. I could replace that 100 with any amount that I put in the bank. And I can replace this 0.1, that's my annual interest rate. I could replace that with whatever interest rate the bank is advertising. So I can generalize this formula to this thing right here. Principal times 1 plus the interest rate over n raised to the nt. And R is the interest rate per year as a decimal. You just change it to a decimal first before you put it in. All right, so before we move on to the next topic, I'm just going to give you an example problem to try at your tables, even though it's not in your packet. Just do it in the margin or on another piece of paper. Okay, so what do I call that model? This is compound interest. This is a model for compound interest. Okay, so how much money is in an account that begins with $1,200, earns 4% interest, compounded weekly, and earns 4% interest compounded weekly for 5 years. So work this out, discuss in your groups, figure out how much money is in this account. Let's see, my formula is A equals P times 1 plus R over N to the NT. And now you just plop in the things that you know, right? Just you're given a bunch of information, put it into the appropriate part of the equation. So I'm going to replace P, the principal, with $1,200. R, my interest rate, I have to change to a decimal, which is 0.04. And divide by N, which is the number of compoundings per year. So that would be 52. And then raise to the NT, so 52 times T, which is 5. So now it's the delicate part is putting this into the calculator and making sure you follow the order of operations. So you can do one thing at a time, or you can put the whole thing in as long as you use parentheses accurately. Okay. So I'll put the whole thing in. So I'm going to do 1,200 times 1 plus 0.04 over 52. So far, this is fine because I want it to do, it's going to do what's in parentheses first. And within the parentheses, it's going to do the division before the addition, which is exactly what I would do by hand, right? So now I want it to raise to the power before it multiplies, and it's going to do that automatically because it knows the order of operations. But I want it to raise to 52 times 5, not raise to the 52 and then multiply by 5. So I have to put parentheses around the 52 times 5. So that's the only little tricky part, is that you have to throw some parentheses there. All right, and so we hit enter, and we get $1,465.57. So we make $265 in 5 years. Yeah. And 4% is even still a little high. Banks don't really pay 4% right now. Okay, so let's see what happens. We already noticed that as we increase the number of compoundings, we make a little bit more money because you get to make interest on your interest. So you make a little bit more money each time you compound more frequently. So in the same example from earlier, where I was investing $100 at 10% interest, and we compounded yearly, twice yearly, quarterly, monthly. You can check these later on your own. If you compound daily or hourly or every minute or every second, these are the amounts that your bank account will be worth. What do you notice about those amounts? It does not go up that much. In fact, it hardly changes at all. Yeah. It is increasing. We are making a teeny bit more money if you look farther out in the decimal places, but for all intents and purposes, you're not making any more money because the bank rounds to the nearest penny. So it does increase forever, but it doesn't increase forever without bound, right? There's some value that it's never going to go above. In fact, it's never going to go above $110.51 because the bank always rounds off the rest. So what's happening is that I'm getting a limiting value. If you look at this table here, 1 plus 1 over n to the n is related to that yearly growth factor. The only thing that's different is that instead of an interest rate there, I have a 1, just because I'm interested in what's going to happen in general. So I just put an easy number to deal with there and see what happens. And as I let n get really big, the value of this growth factor is approaching 2.718. And the rest of the decimals continue to change. It continues to get a little bit bigger, but it never passes 2.718. So that 2.718 number is called E. It's named after a mathematician, Leonhard Euler. It's an irrational number. It's kind of like pi. The decimals go on forever without any repeating patterns. So the natural exponential function is the exponential function f of x equals e to the x. We call it the natural exponential function because this number e pops up so frequently in applications that deal with exponential growth, like compound interest, that it's natural. So we call it the natural exponential function. So here I've graphed it. Y equals e to the x is in pink. And I also graphed 2 to the x and 3 to the x. So does the graph of e to the x kind of make sense in comparison to those two graphs? Yeah. It's between 2 to the x and 3 to the x, which makes sense because e is between 2 and 3. Right? And it's closer to 3 than it is to 2. So e to the x is sandwiched between 3 to the x and 2 to the x. So it's got the same flavor, the same qualitative behavior, just the steepness is a little bit different. All right, so if we could return to our compound interest example, how does E fit into this compounding more and more frequently? So we plug larger and larger values of n into this, my annual growth factor. Plug in once a second, and we got $110.51, and then plus some fraction of a cent. So as n increases, the value of the amount in my account, as I compound more and more often, is going to approach $110.51 and some fraction of a penny, which is approximately 100 times e to the 0.1. So let's put this in the calculator and just verify. $100 times the E button on your calculator is all the way on the left, third button up, the second button. It says e to the x. So you hit second, that button, and it automatically asks you what power you want to raise e to. Because e happens most frequently, it's used as an exponential application. So they ask you what power you want to raise to. We're going to say the 0.1, right? Which was our interest rate. 100 times e to the 0.1 gives me that $110.51 and some little bit of extra cents, fractions of a cent. So a really rigorous proof of why this thing approaches 100 e to the 0.1 is just slightly beyond the level of this course. Maybe you'll talk about it in 108. But we have some empirical evidence that that's what it's approaching. So as n gets large, we think of the compounding as occurring at every single moment or instant in time. You're compounding an infinite number of times each year. And we call this continuous compounding. So this is the key word. When you're solving a problem about interest, if they say the word continuous, you use a different formula than the one we were looking at before. Okay, so for continuous compounding, we use A of t equals p e to the rt. Principal, p is still principal, r is still your interest rate as a decimal, t is still time. Okay, so it differs from the original. This one is the one we use if you have a specific number of times to compound each year, a finite number of times. This new one is for an infinite number of times per year. So here it is again, wrote it all out. Our interest rate per year as a decimal. Okay, so see if you can solve this one. In your groups, you have $1,000 invested for 10 years at a rate of 4% compounded continuously. How much money is in the account? All right, so we plug in the stuff that we know. My principal is $1,000. E is just a number. It's like 2.718, so you just leave it as E. R is 4%, and time is 10 years. So that comes out to approximately so I can type this all in at once here. 1,000 times e to the 0.04 times 10. And you don't, there are less ways to make mistakes with the parentheses in this one. It's kind of a little bit nicer that way. And you get 1491.82. So it's always a good idea to go back and reread the question and say, does this answer make sense? Is this a reasonable amount to expect your bank account to make over 10 years? Yeah. You know, if you had come out with $100,000, you would be like, I think I made a mistake. You know, it's just a good idea to look at your answer and say, yeah, that seems pretty reasonable. Easy little check. Okay, here's another one. Challenge. How long would it take for $1,000 to double if you invested at 4% interest compounded continuously? So same situation as last time, but I want to know how long until I have $2,000. Okay, so it seems like everybody has an equation that they want to solve, right? We start with A equals PE to the RT. We plug in the principal of $1,000. We plug in R as 0.04. The question being how long implies that the variable I'm looking for is T, time. So I'm going to have to leave that as a T because I don't know how long. And how long until that my initial principal of $1,000 doubles and becomes 2,000. So the question is, how do I solve this equation? Okay, so a good first step, because in general, when you're trying to solve an equation, you say, I want to get the t or whatever the variable is by itself, right? So you say, well, I can get rid of this 1,000. And so I have e to the 0.04 t equals 2. I see you're trying to get the e to the 0.04s to cancel. That would work if e to the 0.04 was multiplied all times t, but the t's in the exponent, so they're not going to cancel. Yes, you could rewrite it like that. You could say 2 equals e to the 0.04 raised to the t, right? You could think of that as raising a power to a power because that multiplies exponents. I could raise e to the 0.04. I could just change that to a number. So I could do e to the 0.04, 1.048. 08 to the t. But now it's approximate because I rounded something, which is not a good idea to do until the very end. But we're just trying to brainstorm on how to solve this, so maybe we'll spark something. So I'm trying to figure out, what do I raise 1.0408 to make 2? What does that mean? Yeah, right. So this would say I'm looking for a number that when I multiply times itself t times, I get 2. But t is a unknown, so I can't figure this out, right? I don't know. So we actually don't have an algebraic tool to undo exponentiation yet. We have algebraic tools that can undo multiplication, you divide. To undo addition, you subtract. To undo exponentiation to a number, right? If that thing up there was a number, I could square root both sides. I could take an appropriate root. But when it's a t, I'm stuck. So the only thing I can do today is either guess and check or solve graphically. I know from the previous problem that it takes 10 years to get this $1,000 to almost $1,500. So it's going to be more than 10. Maybe we'll try 20. So what I have is the original equation I wrote was this one. And I have created an equivalent equation, this one. You can guess and check on either of them or on any of the equivalent equations in between. They all have the same solutions. That's what it means to be an equivalent equation. But I'm going to go back to the original because I like thinking about the inputs and the outputs in terms of money in my bank account because it makes it easier for me to guess. So I'm not going to guess and check because it gets to be tedious. I'm going to solve this graphically. Right? We learned how to do that, I don't know, a month or two ago. You make the left side of your equation y1, the right side of your equation y2, and we want to find where the two intersect. So we go to y equals 2,000 and 1,000 e to the 0.04 x. So now I have to choose a window that's going to make sure I can see where they intersect. X is representing time, and I know it takes longer than 10 years, so maybe I'll go 0 to 20. And then Y is the amount of money in the bank account, so I can start at 0. Or maybe I'll start at 1,000, because that's how much money I started with, right? And I need to make sure I can see $2,000, because that's the amount I'm interested in. So maybe I'll go to 3,000, you know, a little bit higher. So I'm looking for where these two intersect, and I do second calculate, intersect, enter, 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 and we get 17.33 years approximately. So very soon, we will be developing the algebraic tool to solve this without using the graphing calculator, to undo raising something to the t. Yes. Today, nothing exists. There will be something. All right, so one last application of exponential functions is actually an exponential decay application with radioactive materials. So the half-life of a substance is the time required for 1/2 of the current amount of the material to decay. So this is our formula for radioactive decay. M of t is the amount at time t. M0, M sub 0 is your initial amount, how much you start with. And then we're going to keep having the amount we start with, right? Because that's what they talk about in half-life. It keeps decaying by 1/2. Okay, so we multiply by 1/2, and the number of times you have your material depends on how many half-lives have passed. So if your half-life is, say, 10 years, and 50 years have passed, that means that the material has halved 5 times, right? So you take the amount of time that has passed and you divide it by the half-life. That tells you how many half-lives have gone by, and that's how many times you have the original amount. So you do M0 times 1/2 to the number of half-lives that have passed. All right, so we'll do one together, then I'll leave you to do one. Tritium has a half-life of about 12 years. It's used to catalyze the reaction in a nuclear weapon. So suppose we have 1 kilogram of tritium. We want to know how much is remaining after 50 years. So I'm going to write down my radioactive decay formula. M0 is my initial amount, which is 1 kilogram. 1/2, because I'm going to half it over and over again. And then T, 50 years have gone by, right? And my half-life is 12 years. So I have to know how many half-lives have passed. So I do 50 divided by 12, and that's 4.166, 25/6. Or 50/12. I'll just, as long as I'm going to write it as a fraction, I might as well not reduce it so you can see where the numbers come from. So then we do 1/2 raised to that power. So we do 0.5 raised to the 50/12 power, and you get 0.05568. Multiply that times your initial amount, which in this case is a 1. So I have 0.0557. Rounded. That's how many kilograms remain. There are 1,000 kilograms in a gram. And now that this is so small, maybe I'll measure it in grams. So that would be 10, 100, 1,000, 55.7 grams. Does that make sense? There are 1,000 grams in a kilogram. So I multiplied this 0.0557 by 1,000. Okay, so you try one. This is another how long, so you're going to have to solve graphically. And I gave you a window to use, but that might not be a good hint depending on how you set up the problem. So maybe just ignore the hint.